Hi, my name is Siddharth Mortil, and I'm a rendering lead with the O3DE Atom team. O3DE is an open source 3D engine, and it can be used to build 3D applications for PC, Linux, Mac, Android, and iOS. For this talk, I will be going over how to debug GPU and basically any issues around GPU. Specifically, I will be pointing out tools that you can use to help debug GPU crashes. If you have a timeout, TDR, or a device lost, I can point out tools that you can use to isolate exactly which path caused the GPU to crash. We'll also take a look at tools to help profile the GPU, so figure out exactly which passes are running inefficiently and how to optimize those passes. And we'll also take a look at how to debug rendering artifacts. So which paths introduce a rendering artifact and how to debug that. Let's start with GPU crashes. So we have a couple of ways, a few ways to help debug GPU crashes. So we have GPU validation layer that can be enabled across all the backends, DX12, Vulkan, and Metal, and it works across all the platforms, Windows, Linux, Android, Mac, and iOS. We have a GPU-CPU sync mode, which lets the CPU run in lockstep with the GPU, and it's also implemented across all the backends, DX12, Vulkan, Metal, and it works across all the platforms. We also have integration for Dred, which works with DX12, and we have Nsight Aftermath, which is the Nvidia tool, and it works for the Nvidia hardware on DX12 and Vulkan for Windows and Linux. I've also pointed out a command line parameter that you can use to pick a specific GPU, especially if you have multiple GPUs on your machine. Imagine, if you will, if you have, let's say, Nvidia and AMD, and you can use -force adapter equals the vendor name, and it will make sure to use that card for its usage. Let's go over GPU device validation. So for DX12 and Vulkan, you can enable device validation by using this command line parameter, -RHI-device -validation equals enable. And for Metal, you can use edit scheme run options GPU frame capture to Metal, edit scheme run diagnostics API validation enabled. And that's for the XCode on the XCode IDE for Mac. So when you enable this, what does it do under the hood? When you enable this validation, under the hood it enables the validation layer, which runs extra validation around each function call. So if you're misusing the function call or there's some sort of invalidation error around it, it will output that error in the output log. So you can check the output log and make sure that that you don't have anything that looks suspicious. I have a demo for each of these tools to help you better understand how all of this stuff works. Let's start with a demo for the device validation. So in this case, I'm going to quickly launch automated testing.game launcher, which comes with the core engine, just to quickly show how to enable device validation at the RHI level. So in this case, I've added -RHI-device -validation equals enable. What this does is it will enable the validation layer for both DX12. It works on DX12 and Vulkan. Since I'm using Vulkan in this case, the Vulkan validation layer will hook into every Vulkan function call and basically provide validation around the API usage. And if there's a crash or if there's a misuse, it should throw out warnings or errors in the output window. So in this case, I have the app running, and it's already spit out a couple of warnings here. So anything that says VK debug message, that means it's a message that came from the validation layer. In this case, it's saying that a vertex attribute at location 3 is not consumed by the vertex shader, so that means we probably are sending data that we may not need to, and it can cause performance issues. Scroll up, there's an error. The last one was a warning. So errors are more significant, and it could possibly lead to a GPU crash. What it's saying here, in this case, you have a structure. Okay, so this is the image interface of DDGI. So it's related to ray tracing for our global illumination diffuse probes. You have a structure in the shader whose alignment doesn't match with what we're binding on the runtime side. So yeah, so this is good usage of the command line arguments to see if the validation can catch errors that sometimes can be fatal, especially if you have a function API call that crashes on the CPU, then it will output some form of an assert or a warning before it crashes. If it's a crash on the GPU, then if you're lucky, it may provide some clues as to some misuse that may have caused the GPU crash, but it's not 100%. And that's it for this demo. Okay, so for the next tool, we're going to be going over the GPU-CPU sync mode. Atom is the render used by the O3DE, and it has triple buffering support between the CPU and the GPU. And it's dictated by this variable called frame count max. So if you reduce that number to 1, that means there is no buffering. So CPU will block after every frame until the GPU finishes. So the fact that it's 3 is set to 3 means the CPU can run up to 3 frames ahead of the GPU. So if there's a GPU spike, it doesn't spike the CPU. It can continue running, and it provides a better gameplay experience. So how does that work under the hood? So imagine, if you will, if CPU encodes GPU commands for frame n at time t0, it sends it to the GPU, and if the GPU is only 1 frame behind, it will actually execute those commands on time t1. And the same thing happens with frame n plus 1 and then n plus 2. So this is the behavior you'll see if the GPU is exactly 1 frame behind the CPU. Well, what happens when the GPU crashes? So imagine you have frame n that is encoding GPU commands. And in this commands, you have a draw call that has PSO, and it has shader bytecode that has a crash in it. So there's some sort of a stall. It's reading from bad memory. So the GPU crashes at time t1. Because we have triple buffering, CPU will continue encoding GPU commands. So we'll continue encoding GPU commands, and then when it's 3 frames ahead, it will wait for the GPU to signal back and say, hey, I'm done with the work for frame n. Because the GPU has crashed, CPU essentially gets hung because it gets a device lost error message, and then it can't proceed anymore. The point that I'm making here is that CPU crashes at a point where it's completely not helpful. So in the debugger, it will break, but the call stack is not useful because it will be pointing at either the end of the frame where it's waiting for the GPU to finish, or it breaks at some random API call where it's not helpful at all. So how do we debug GPU crash? Where you don't have a call stack, you have no idea, your device validation layer didn't point out anything suspicious. So we've built in this GPU-CPU synchronization mode. So first thing you do is you enable this macro, az_force_CPU_GPU_insync. It's located in this file, base.h. You recompile and you run the app. What this macro does is it forces each pass into its own command list, and then CPU essentially for the same frame runs in lockstep with the GPU. So for each command list, it will encode a bunch of commands, send it to the GPU, and then waits. It waits until the GPU says it finished executing that command list, and then it will move on to the next command list, the CL2, and then it will encode it, call execute, wait until GPU signals back and says, okay, I'm done executing this command list, and so on and so forth. So what happens when there's a GPU crash? Well, when there's a GPU crash, so imagine, if you will, CL2, CPU encoded CL2, which has a crash in it. It sends it to the GPU. GPU will execute it and never signal back to the CPU. So now CPU is essentially hung, waiting for GPU to respond back, and it didn't respond back. So now CPU will break in the IDE, and you'll have the perfect call stack, and you'll know exactly what commands were being run when the GPU crashed. Now I'll go over a quick demo to show how to use this mode to help debug GPU crashes. So for this demo, I've added a stall in the full screen shadow shader. So the full screen shadow pass should crash. Okay, so for this clip, I'll show how you can use the CPU-GPU sync mode to help debug GPU crashes. The first thing you want to do is go to base.h, the one that lives inside atom rhi.reflect, and you want to go to this macro and enable that. Comment it out, so you can comment it, recompile, and rerun. And what this macro does under the hood is it will make sure that when CPU is encoding GPU commands, it will have one command list per pass. So for one command list, it will encode all the GPU commands for the pass that's the next in line, and then it will call execute on the command list on the CPU, and then it will wait for the GPU to signal back using a fence or whatever the synchronization construct we have set up to say, hey, I finished executing this command list. And that tells the CPU to know that, hey, this command list was valid, it worked, there was no crashes associated with it, let's move on to the next command list. So it goes from one command list to the next one, to the next one. So if you have 10 passes, it will do this 10 times for the whole frame. So that way, when the GPU crashes, the CPU will basically crash, and it will know, or it will catch the crash, and it will know GPU was working on this command list, which was working on this pass, and it will output that information. So let's run this app right now. It will run this app, it will immediately crash on the first frame, or at least the GPU will crash, and the CPU will hopefully catch the crash. Let's wait for it to do that. Okay, so we have actually crashed on the GPU, and the CPU is displaying this dialog box. The dialog box basically says the GPU device was removed while working on the specific pass. In this case, is the full screen shadow pass, which is correct. So the CPU recognized that the command list that had encoded and called execute on the full screen shadow pass has not signaled back. So that means that's the one with the problem here, and the CPU has displayed this dialog box. So I'm going to and now it will break on the CPU in my debugger. And this call stack is valid. So if you know your way around the RHI, if you can stop at the frame graph executor : end group, this is where we actually call execute, and we're basically waiting. The CPU is waiting for the GPU to signal back. And this call stack is valid, and it lets you inspect everything that all the data that we currently have on the CPU, and you can inspect the command list data and all the resources that were sent to the GPU in a way to make sure that they're all valid and there wasn't anything that might seem wrong right off the bat. So you can open up your group, which in this case is a frame graph execute group. You can open up a context. In this case, it's only one context. You can open up a descriptor. It shows you it was working on the full screen shadow pass. The command list, essentially, you can open up the VK Vulkan command list. It has your state here. The state has information around PSOs, your scissors, viewport. You can even take a look at submit range. You can take a look at, you can even take a look at the scope itself. So if you just collapse everything and you open up the actual frame graph group, there's only one scope. You can open up the scope. Scope in this case is a pass. So all the data around the pass, all the image attachments, buffer attachments, your barriers, your load store actions, clear requests, everything is captured here. And you can traverse through this data and make sure that it all looks legit. With GPU crashes, the hardest part is actually figuring out what work was it that crashed the GPU. So this is a really good way. If you have a GPU crash, this is sort of my first step that I always take to figure out, hey, if I can repro this crash in this mode, it will immediately tell me what was the work that was causing the GPU to crash. Now, it is possible that your GPU crashed due to some memory stomp or memory issue, in which case you may not, or some sort of a timing issue, in which case you may not be able to repro the crash in this mode. And if that happens, then you'll basically have to resort to using Dred for DX12 or Aftermath for Vulkan. You basically are sort of out of luck with this mode, but there are other tools that you can use to help try and figure out, hey, why did my GPU crash? And that's it. Okay, so for this next part, we will be going over Dred. Dred stands for Device Removal Extended Data. It's an API provided by Microsoft to essentially embed breadcrumbs into the GPU command stream, and it essentially tracks the progress of the GPU work right before the GPU crash. So you can embed a breadcrumb for each render operation, and then when it crashes, it will output all of into the log all the operations that took place right before the TDR happened. And then that way you can get a pretty good idea of what the GPU was doing at the time of the crash. Here's a quick demo to go over how it actually works. Okay, so for this clip, I'm going to demo how we can use Dred to do debugging for GPU crashes. So Dred is only available on DX12, so this would only work on platforms that have DX12 support. So I am going to be running the automated testing.game launcher. This is a sample project that comes with a core engine. The first thing I want to make sure that we're actually running the DX12 backend, because on PC you have both DX12 and Vulkan backend support. So I'm basically saying -rhi equals DX12. This will make sure the DX12 backend is running, and I'm going to run the app. The first thing that I did was I introduced a long stall in one of the passes, full screen shadow pass. So I modified the shader and added up this long stall for the full screen shadow pass, or shadow shader. And it should crash on the GPU on the first frame. So the GPU should crash on the first frame, and then the CPU should crash on a couple of frames after, which is exactly what we're seeing here. We see a GPU device was removed. This is a CPU crash showing a dialog box that says the GPU has crashed. You can press OK, and you can kind of see that the CPU is essentially it captured the GPU crash. It hasn't actually fully crashed here. It's telling the user that, hey, the GPU has crashed, the CPU can't really continue, so you can do stuff like save your content. But if you look at the main thread, you can kind of see CPU is essentially hung on a signal from GPU, in this case, our fence. So what happens when the GPU crashes? So we actually have code in our DX12 backend that actually writes out the breadcrumbs related to Dred. And those breadcrumbs, yeah, this is all the code. It's all captured in the device on device removed. These breadcrumbs can be seen in a log file. So you open up your user folder, and then there's a folder called .O3DE. Open that up. There's a folder called logs. There's a folder called Dred. And here's a log file that was automatically created. You don't need to do anything special here. You open that up. You want to look for the string called error start. A bunch of crumbs. You want to see which crumbs happened right after the error start. So this is right here. So you kind of see error start, and the first breadcrumb after that is a draw call, draw instance. So you know this draw call came from this pass, which is the full screen shadow pass. So you know the problems with the full screen shadow pass. So if you're a graphics engineer, you can start looking at this specific pass, start looking at the shaders, start looking at what this pass is doing, make sure everything is correct. If you're a content developer, you can use this and essentially create a GitHub issue and assign it to the engineer that is most familiar with this pass. And that's pretty much it. Okay, so now we're on tool number 4, which is Nsight Aftermath. This is a tool that was provided by Nvidia. And in order to enable it, you have to enable it during the configure step. So during configure, you have to provide it the path to the Aftermath's the SDK directory. Once you've done that, it automatically enables all the Aftermath related code. It only works for the Nvidia hardware, and it should work with DX12 and Vulkan backend. There is some more information at this website on GitHub, so you can go there to get the latest steps. But I'm actually going to be showing a demo on how to use this tool in the next slide. Okay, so for this demo, I will show how you can use NVIDIA Aftermath to help debug GPU crashes. Hopefully you've configured the solution with the correct ly CMake option. You have to pass in with the path to the Aftermath folder. And once that's done, it should automatically enable use Nsight Aftermath macro. And that means that once the GPU crash happens, it will automatically dump out a log file in the executable folder. So in this case, I'm going to be running automated testing.game launcher. I will make sure that we're running the Vulkan RHI, because in this case, I want to run Vulkan and use Aftermath using Vulkan. On DX12, we already have Dred. I've already added a stall inside the full screen shadow shader. So that path should crash on the GPU on the first frame. and then hopefully in the subsequent frames, the CPU should hang, and Nvidia Nsight should dump out a log that we could hopefully use to analyze the GPU crash. So in this case, it's launching the app, it's going to render, and immediately the CPU is hung. And you can check the output log. It should say device lost right here. OpenAPI method failed, device lost. That means the GPU has crashed. Let's open the executable folder. So we go to the automated testing, build, US 2019, bin, profile. Right here, it just now created these 3 files. So you want to load the NV GPU DNP file, and you want to use the Nsight graphics app, because that's what can load this file. You look at the crash info, and immediately you can see the command key that was running. Actually, this one says it finished, this one says it not started, so it's not very helpful. But you can see which shader was running. So in this case, it was running the full screen shadow shader. So that means something's probably wrong with that path. If you're a graphics engineer, that's where you will start the investigation. And if you are a content developer or not a graphics engineer, you can create a GitHub issue and tag this path as a possible suspect for the GPU crash, and go from there. And that's it. Thank you. Next, we will take a look at GPU profiling and what tools we can use for profiling the GPU on your specific platform backend. So we have a few tools here. We'll go over PIX, Nvidia Nsight, RenderDoc, and the in-game profiler. I've mentioned XCode. There is no demo for this specific talk, but I may do a future talk where I can go over XCode in detail. So PIX is available on DX12 for Windows. Nvidia Nsight is available on DX12 and Vulkan. It applies to Windows and Linux. RenderDoc is available on, again, DX12 and Vulkan, and it's available on Windows, Linux, and Android. And the in-game profiler works on all backends, and it only works on the Steam platforms at the moment for Windows, Linux, and Mac. It does not work on the mobile platforms because mobile platforms use TBDI GPUs, so doing very accurate timestamp-based queries don't work. Let's take a look at PIX. In order to get PIX to work, you have to install PIX. And there's a link where you can install PIX. You'll have to download WinPix event runtime. You will have to configure your O3DE application with the following CMake options. And so it's DLY PIX enabled equals on, DLY PIX path equals wherever you have downloaded and unzipped WinPix event runtime. You will launch PIX as the administrator, and you'll use the following command line parameter, -enable PIX GPU. For detailed information, you can go to the GitHub website and follow the steps there. Next, we'll go over a demo of PIX. Okay, so for this clip, I will be going over how we can use PIX to do GPU profiling. You want to launch PIX as an administrator. In here, I already have the executable set up, and I'm using the command line prompts plus low level equals default level. This is the automated testing game launcher. The RHI is DX12. That's PIX enabled with DX12. And I'm using enable PIX GPU. This makes sure that the markers and everything get set up correctly. You want to launch it for GPU capture. You just essentially launch. This should load the application. In this case, it's just a very simple scene with a shader ball. You want to do the GPU capture. You can actually capture multiple frames, or there's a couple of options you can play on. But in this case, it's from I want to capture one frame from one present to another, and then I'm going to load the capture. So in this case, if you have everything set up correctly, you can actually start the analysis. If this crashes out or doesn't work, then just update your PIX and update your drivers. That usually fixes any issues around replay not working. And this may take some time, but in this case it didn't. It's actually pretty fast. You can see all the, so in this case I'm only interested in the graphics Q0. I'm not really interested in graphics or compute, other graphics queues or compute or copy queues, because there's not a lot of work going on there. So I can see all if my markers are enabled, I can see all my passes here and all the draw calls in the passes. So you can immediately see this is the whole frame. So you can kind of see that you have full screen shadow pass taking a one big draw call here. TOP to EOP means top of the pipe to the end of the pipe. So in this case, it's taking about 600 microseconds. Then your culling pass is taking, decent amount of time. Forward pass is taking decent amount of time. So let's quickly go through and investigate why. So you want to collect all the counters here. So you basically go through and enable all of these counters. It's taking some time here. Let's just give it a few seconds. So, okay, so it finally came back after finishing its work. So it is working now. Okay, so I've collected all the counters. So what we want to see is take a look at the draw call that's taking a lot of time and see why. If you click on this and you scroll down and you want to scroll down to the wave distribution section. The wave distribution essentially shows how many warps are being run. Green usually means that we're leaving a lot of warps unallocated because the drivers were not able to launch them. And then we need to figure out why. Like, why couldn't we launch more? The more waves are launched, that means it'll take less time, the whole draw call. You scroll down, you can kind of see that, oh, there's a lot of work going on, ALU work going on, there's a lot of FMA heavy pipes, a lot of floating point math arithmetic is going on. Oh, here we go. PS warps can't launch. So it actually just tells you it's blocked 99% because of register allocation. So your number of cycles where PS warp launch was stalled due to register allocation. So basically your shaders are using a lot of registers, and we need to essentially reduce the number of registers used, and that will let the drivers launch more warps and reduce the total number of time taken. So that's why this is taking a lot of time. Let's take a look at a couple of other draw calls. So in this case, the light culling pass. Light culling pass, you take a look at, oh, okay, well, warps it's pretty good. Like, there's very few room for improvement in terms of warps. Well, then if the GPU is really busy and all the warps are launched, why is any room for improvement there? So we take a look at some of the other statistics. So ALU pipe is pretty good. A lot of math, a lot of floating point math going on. That's U pipe. Let's see. Okay, CS warp can't launch. Okay, here we go. So basically, it's saying that you can get some little bit better performance by reducing your register usage and your SHMEM allocation. So let's look at this. I think it's the shared memory. Yeah, so CS warp launch was stalled due to SHMEM allocation. So I guess the shader is probably using a lot of shared memory, and that's causing stalls in certain places. So there is some room for improvement if you take a look at the shader and see if we can reduce our usage of shared memory, and obviously reduce the number of register count. So let's take a look at the forward pass. Okay, forward pass is the draw call, one of the draw calls, which is taking a long time. And same thing, let's look at the PS warps can't launch. There's only one big reason, and it's a register allocation. Very similar to the shadow pass. So reduce register count for your shaders, and this should have an impact here. Let's take a look at one more. SSAO compute. So SSAO compute is basically, okay, very similar. You can see the same pattern here. It'll benefit a little bit from register, benefit a little bit from SHMEM allocation, but for the most part, there is some room for improvement. There's a little bit of green area here. So yeah, the SSAO compute will actually, in fact, if you're going to spend time, I would rather spend time on SSAO compute versus light culling, because if you look at it, SSAO compute has more green. That means if you take some action, it will be able to launch a little bit more warps. Yeah, so that's pretty much how you can use PIX as a way to get better insight into what the GPU is doing for each pass. And PIX is actually really good at, if you're using a lot of async compute, you can actually switch to different other queues, which is not very easy to do, I find, in other profilers. So I usually use PIX for that every time I'm using any experiments with async compute. And that's pretty much it. Thank you. Next, we will take a look at Nvidia Nsight. Nvidia Nsight is a tool provided by Nvidia, so it only works on Nvidia hardware, and it shouldn't work on Windows and Linux. You will want to download the Nsight application. You would configure O3DE with PIX enabled. This enables the PIX markers in the code, and Nsight is able to use pix markers for its own GPU captures. So when you use GPU capture, all the command lists, all the passes will be named correctly. You would want to launch Nsight as an administrator, as that allows the GPU the really low-level GPU counters to work correctly. Next, let's look at the demo of Nsight for profiling. Okay, so for this clip, I will be demoing how to use Nsight for GPU profiling. First thing you want to do is launch it as an administrator, because this allows you to capture advanced GPU counters. Create a new project, name it test project. I will assign an executable. In this case, the executable is the automated testing game launcher that comes with the core engine. And I will be passing in command line prompts, which in this case is the load level, default level, which is the shader ball level, and the RHI is DX12. I'm using GPU trace profiler with advanced mode metrics. So launch the GPU trace. This will hopefully launch the application. Wait for the application to load. So very simple scene, nothing fancy going on here. You generate the GPU trace capture. The point of this clip is not to help you analyze some really complex thing, is to just quickly show you how to use Nsight to get a really good insight into where all the work's going for a frame. So immediately you'll see all the command lists at the top that ran for this frame. And to make sure that the markers are working, you can look at all the passes, and all of these passes are named correctly. So this one is a shadow pass. This one is vertical blur pass. So that means the markers are working. If the markers are not working, configure your application with pix enabled. So the first thing I immediately do, I can use the right-hand section to look at the unit throughputs to get a better idea of what the GPU is doing under the hood for the pass. But what I actually prefer is looking at it in the analysis view. The analysis view is really cool. If you expand the left side column, you'll immediately get a good understanding of the whole frame. So these are all the passes that are being run on the frame. And with each pass, you can see the exact percentage that it's the footprint of that pass for the whole frame. So obviously, if you optimize a pass that's already has a very small footprint, the impact it will have over the whole frame will be extremely small. So you want to take a look at passes that have large footprints. So in this case, a full screen shadow pass that is taking up almost 6% of the frame. So let's take a look at why and where the bottleneck is. So if you double click, it will actually show all the throughputs on the right hand side. So immediately you can see, first thing I actually look at is the SM occupancy. It shows how many warps are being launched on the shader core for this pass. So usually like light gray and dark gray means that you have warps that are not being launched. Like no work is being it's not optimal, and not all the warps are being launched. So if you open up all of these tabs can show you where all the bottlenecks are. So in this case, the SM throughput is 65.6. And if you open up the SM warp occupancy tab, it will tell you where the bottleneck is. So in this case, it's PS warp launch stalled by register allocation. So the shader for this pass is using up a lot of registers. And because it's using a lot of registers, it's unable to launch a large amount of warps. So the existing number of warps that are in motion have used up all the registers. So in order to get more green, essentially, you want to reduce the number of registers used by the shaders. And there are certain things you can do. They actually have some ideas here that you can follow. So another pass that we can, let's take a look at a few more passes. So here's a shadow vertical blur. So we're doing a vertical blur on the shadow texture. And that should not take 6% of the frame. So there's something weird going on here. So if you double click on the thing, here it shows up. Oh, wow. Okay, so basically light gray means no warps are being dispatched. So it's literally the GPU is sitting idle, not doing anything. The warps are not being run. It's doing, I think, it's bound by L throughput. Okay, it's stalled by long score bit. So it's basically bringing in memory, probably related to the shadow maps. So it's waiting for the shadow maps to come into the GPU memory, which is kind of weird. But yeah, so it sounds like it's doing a memory transfer for the first 60% of the pass, and then the warps are being launched to do the actual blur And that blur only takes the last 40%. So we should be able to figure out and remove ideally the first 60% of this stall and get a big performance gain back. So let's look at other patches. Okay, so these are forward patch. Forward patch is only taking, so that's actually pretty good. Forward patch is where we're doing all the lighting and shading. The fact that it's only taking 6.6% is pretty good. So if you look at it, there is still a lot of dark gray here, which means that we can launch more warps here. We're leaving some performance on the table. And again, it's stalled by register allocation. Same idea as the full screen shadow pass. The shader is using a lot of registers, and because it's using a lot of registers, it's stalled by the number of register count. So if you can reduce the number of register count by the shader, it will actually increase performance on this pass. Yeah. So let's take a look at a few more passes here. So now we have scatter distance pass. This also is taking 6.5%. It's bound by multiple things. It's bound by the register count, it's bound by shared memory size, and it's bound by warp slots. So, we can take a look at all three of them separately and figure out, hey, how can we make it more performant? Oh, wow, this merge pass is taking 9.3%. So it's bound by crop. So crop is the color ROP throughput. It's basically bound by register count for the compute shader. So the compute shader is using up a lot of registers, so it's unable to dispatch more warps. So yeah, so basically this is a really good tool to get a really quick idea of what the GPU is doing under the hood for each pass, what the bottlenecks are, and where to start investigating and creating a performance plan where we can have the biggest impact and actually help reduce the total GPU frame time. And that's it for the clip. Next, we will look at RenderDoc. RenderDoc works on Windows, Linux, and Android, and it works on DX12 and Vulkan backend. You can download RenderDoc at the mentioned link here, and you will want to configure RenderDoc with PIX enabled as well as RenderDoc enabled. The PIX markers are used by RenderDoc for its own GPU instrumentation, and you will want to provide it a path to where RenderDoc was downloaded to. When launched, you would want to provide the following command line options: -enable RenderDoc. Next, let's look at a demo where we use RenderDoc for profiling. Okay, so for this clip, I'll be showing how we can use RenderDoc to capture some profiling data from the GPU. It's not the best tool, since there are better tools like Nsight and PIX, but RenderDoc works across all the platforms. So for that reason, it can actually be a decent tool to just get a very high-level idea on where the GPU time is going. So in this case, I'm going to attach the the automated testing game launcher configuration executable. I'll pass in the command line prompts, in this case, which level to load, which is the default level, and which RHI to run, which is the X12 RHI. To launch the application, which is just standard level, default level with the shader ball, and I will capture the frame. And once the frame is captured, you can open it up, and what you're looking for is under Window, there's a menu called Performance Counter Viewer. You can open that up. You can capture counters. There are built-in counters in here, and you can sample them. So here, this is essentially what a high-level view of where the GPU time spent. So you can sort it by GPU duration, and you can kind of see which event ID yielded the most, took the most amount of time. So in this case, it is a draw call under the full screen shadow pass. The full screen shadow pass is taking a lot of time. You can get some other information like samples passed, pixel invocations, but really these are really high level counters. So you can't really get deeper insights into what's going on in the past, where the bottlenecks are. Is it memory dependency? Is it the number of register allocation? Is it a long scoreboard or short scoreboard? Any of that information is not available in RenderDoc. For that, you'll have to go to Nsight. Let's take another look at another event. In this case, this is a forward pass. It actually gives you GPU time per draw call. So it actually, 533 took 581 microseconds, I think, and 541 took 145. So you have pretty decent information in terms of how much time each draw call took. So you can use that to get better insight into how RenderDoc can give you better profiling data. And that's it for this clip. Thank you. Next, let's take a look at the in-game profiler. The in-game profiler is implemented on DX12, Vulkan, and Metal, and it works on Steam platforms PC, Linux, and Mac. It does not work on the mobile platforms Android and iOS. And it's mainly because mobile platforms use TBDR GPUs, where it's not an immediate form of rendering. You can't do very accurate timestamp-based queries. So if your command list is encoding work for multiple passes, it's really hard for you to capture the exact time taken for these passes. I think on Metal, you are allowed to extract time taken per encoder, but you can do more fine-grained timing profiling. In order to enable in-game profiler, you have to press Control plus Home. It brings up the in-game menu, and then once the in-game menu is out, you can click on Atom Tools and then pick GPU Profiler. Here's a quick demo to show how it works. Okay, so for this clip, I'm going to be using the in-game GPU Profiler to help you diagnose where all the time is going on the GPU, like which passes take how much time. So I'm launching the automated testing game launcher with the default level, and the RHI is Vulkan. But really, the in-game profiler works on DX12, Metal, and Vulkan, and it works on all the Steam platforms. So PC, Linux, and Mac. So I'm launching the application. This is a very simple scene with a shader ball, and I'm going to be using the in-game GPU profiler uses ImGUI. So you have to activate the ImGUI profiler. So for that, you press Control and Home. So right at the top, the ImGUI profiler menu shows up. So in here, you'll go to Atom Tools and then GPU profiler. So you have three options here. The option that is most applicable here is the Enable Timestamp View. It will open up a menu. It is now capturing data for each path. It uses the timestamp queries and uses the timestamp queries to track how long each pass takes. And you can actually pause the capture so that you can see the data. The numbers are not changing every frame. And you can sort of scroll down and see all the passes here. I already know in this case that the shadow pass and the forward pass take a decent amount of time. So if I go down here, you go full screen pass takes 0.25 milliseconds. I mean, if you think about it, this is a 3.3 millisecond frame. So 3.3 milliseconds, the full screen pass is taking about 0.25 milliseconds. Then your forward pass is taking about, let's see if you can find it, 0.28. So those are the big ones. But, you can sort of scroll down. You can see like SSAO compute takes almost 0.1. There is also, here we have depth to linear, the resolve. So there's a whole bunch of passes. So this will give you a really quick idea of where the GPU time is going for your scene. Now let's close this. There's another thing I want to show you is the Enable Pipeline Statistics view. If you enable that, it will show you all the inbuilt pipeline statistics counters that are exposed by the DX12 Metal and the Vulkan API. So in this case, for each pass, you can track the vertex count, primitive count, vertex shader invocations, pixel shader invocations, the compute shader invocations, all of this data. So this is same data that you can actually capture on the RenderDoc, but in this case, it's in-game, so it's really easy to see. So for some people, this may be beneficial. And the last view is enable GPU memory view. This is to essentially see GPU memory and see where that. So it's not. It is beneficial for GPU profiling if you think that the cause of your slowdown is the GPU memory usage. You can actually press capture, and then you can track all the pools and the allocations around it. And that's it for the thing. Actually, one more thing I wanted to show is the GPU profiler. Oh, okay, you can actually say, oh yeah, we should add functionality. Oh yeah, so you can actually show the timeline. So you can actually see the whole frame in this timeline mode. So to really easily assess where all the big passes are. The full screen shadow path is a big rectangle, so you know that's where all the time is going. And yeah, that's it. Next, let's take a look at XCode. XCode is the IDE provided by Apple to do any sort of development on Mac and iOS. For this talk, I have not provided a demo for XCode, but it does work. The Metal backend has support for markers, for encoders, Metal encoders. So you should be able to do GPU capture by pressing on the camera button, and you should be able to inspect all the passes in the GPU capture and take a look at GPU counters and get insights into which passes are taking a long time and where the bottleneck is. In future, I will probably provide a demo to show how we can use XCode for any sort of GPU profiling sort of investigation. Next, we will take a look at GPU rendering artifacts. For this part of the talk, I will be going over tools that you can use for your platform to help investigate your GPU-related bugs. So if you have, let's say, black pixels or something that doesn't look right, you can use these tools to help do GPU capture and investigate data related to every pass in your frame. So we have a few tools here, very similar to the GPU profiling section. We have Pix, Nvidia Nsight, RenderDoc, in-game pass tree viewer, and XCode. I have not attached an XCode demo with this talk, and that may come in a future date. Pix is supported on DX12 for Windows platform. Nvidia Nsight is supported on all the Nvidia hardware for DX12 and Vulkan, and it works for platforms Windows and Linux. RenderDoc is supported on all hardware. It should work for DX12 and Vulkan, and for platforms Windows, Linux, and Android. In-game pass tree viewer is implemented on DX12, Vulkan, and Metal. Although I do recommend using it for the Steam platforms only, Windows, Linux, and Mac, and not really for mobile. And the reason for that is you need pretty high screen real estate to be able to traverse the pass tree and to be able to see the attachments. It's much harder to do on mobile, and most likely you need some form of like an off-screen viewer, which we currently don't have. For Xcode, the markers still work. So doing a GPU capture using the camera icon would still work. So in theory, it should work. It's just there's no demo for it as part of this talk. Next, let's take a look at Pix. In order to use Pix for debugging rendering artifacts, you will want to install Pix, download WinPix event runtime and unzip it, configure O3DE with the following CMake options: -dly_pix_enabled equals on, -dly_pix_path equals the folder where WinPix event runtime was unzipped. You will want to launch Pix as an administrator, and use the following command line param: -enable pix GPU. Detailed steps are provided at the GitHub O3DE GitHub wiki page. Next, let's take a look at a Pix demo for debugging rendering artifacts. Okay, so for this clip, I'll show how we can use Pix to debug rendering artifacts. So I've launched Pix as an administrator. I already have the executable set up. The command line arguments is an automated testing game launcher. I'm loading the default level, RHI's DX12, and I'm passing in -enable pix GPU to make sure all the Pix markers are launched correctly. I'm launching it for GPU capture. So I'll launch the actual application. It's a very simple scene with a shader ball. I will do a GPU capture from present to present. So this is one frame. You can capture multiple frames, but in this case, I'm just going to show one frame. And once it's started, you can start the analysis. If the analysis fails or something goes wrong here, just make sure you update the drivers and get the latest version of the Pix. So immediately you know the markers are working because you can see all the names here for all the patches. So that's great. The reason why you see a bunch of merged. So the way Atom encodes GPU commands is that it creates multiple command lists, and each command list can do work for multiple patches. So in this case, you'll see one command list which is grouped in this one group, and it's doing the work for all of these patches. It's encoding commands for all of these patches, and then you can have second command list doing these patches, and then imagine, if you will, you can have what you don't want is one command list doing one patch. That's very inefficient. So in this case, let's take a look at the forward path, because forward path is, let's imagine, if you will, that forward path is where our bug is. So we open up the opaque forward path. There are two draw calls here. Let's find the draw call for the mesh. So in this case, I will click on, I think the second one is the mesh, but you can actually just quickly confirm by taking a look at the output. So this is the VS output. Yeah, this is the shader wall. Usually the problem whenever it's in rendering artifact, for the most time, it's with the resources. So something got messed up with what we bound, or there's a problem with the shader itself. So in order to quickly see that the pipeline state and all the resources bound are correct, you can just open up we can go inside the pipeline like that. So before, you may be in a different place, like an overview mode. You don't really care about collecting counters in this mode. This is more for profiling. So you'll go to the pipeline tab, and in here you click on the draw call, and then you can see the state. So this is your root signature. And then these are all the descriptor tables, the CBVs, constant buffers that we're bounding, and the static samplers. So you can essentially click on them directly. So this one points to right here, CBV. This is an object SRG constant buffer. This is its definition. So it's really great. You can actually just open it up, and you can see all the values here. So it's great to make sure that the data that's going in all the constant buffers is accurate. Then you want to take a look at this SRVs. So in this case, we have an SRV here that is captured in pixels. Oh, okay, so this is okay. So we can actually click on this, and this is used for the pixel shader. And in this case, it's just the albedo texture. But even on the pixel shader, there are constant buffer views that you can take a look at. So this is the object SRG, this is the material view, scene, and this is the definition. So Pix is great. Like, you can see all the resources. You can look at the output. So this is the render target 0. Oh, I need to zoom out a little bit. So render target 0, which is the output. Then you have your albedo. You have the normal. So you can actually, and if you want to know, yeah, here we go. Okay, the diffuse, specular, albedo, F0 specular, which is used later on in further patches. You have your depth stencil. So yeah, you can actually use this to make sure that the inputs and outputs for each path are accurate, and this way essentially debug any rendering artifacts that can happen for your frame. And that's it for this clip. Next, we will take a look at Nvidia Nsight. It's a tool provided by Nvidia and only works for Nvidia hardware. You can download Nsight at the link provided in this slide. The Nvidia Nsight tool can be used for GPU profiling investigation and also for rendering artifacts related investigation. So you will want to configure your O3DE app with CMake options to enable PICs. That's because Nsight uses PICs markers under the hood for its GPU instrumentation. You will want to launch the Nsight as an administrator, and that's pretty much it. Next, I'll show a quick demo on how to use Nsight to help debug specific passes. Okay, so for this clip, I will be showing how we can use Nsight to help debug GPU rendering artifacts. In this case, I'm going to launch it as an administrator. Quick launch, automated testing.game launcher with the default level and the RHIS DX12. This is, since I'm debugging the frame, I want to use the frame debugger, and I launch the frame debugger. This will launch the application, which is a very simple scene. It's a shader ball scene. So now I can press F11 to capture the frame, and it will go into this special mode where I can actually now traverse the whole frame. So if you look at the bottom, you can see the pass name, and I can go up and down the whole frame. So initially, this is the depth pre-pass. After the depth pre-pass, it does a resolve, camera motion, min, max. These are all the shadow cascades. If I keep traversing, this is the full screen shadow pass. Then you have your forward pass, SSAO compute. Then I have your UI, 2D, OxGeom, and a copy to swap to. So let's say there was an artifact with the forward pass. So let's say I've identified that there's a problem with the forward pass. So I'll stop at the forward pass. Let's say the problem is with the shader ball. So I'll stop at the draw call where we rendered the shader ball, and then I'll go back to the Nvidia Nsight. In this case, the layout sometimes gets messed up. So let's go back to, let's repick the event, because it should automatically take you to that exact event. If I now head back to Nsight graphics, boom, 757. So it's already pointing to the exact draw call. And you can confirm that because it's right under the opaque, the forward pass. So if you expand it, this is the opaque forward pass. And then this is all the information that I have. Let's say I've already isolated that there's something wrong with the shading here. I can see all the render targets, so color 0, color 1, color 2, depth stencil. I can access the input assembler, vertex shader, pixel shader, and your output merger. So for the vertex, let's say the problem is with the pixel shader. So you can actually see if you have shader debug symbols and you've attached them, you can actually see the shader source code right here, which is very helpful. You can see all the constant buffers that were attached. So these are all the draw sRG constant buffer, object, material, view, scene. I wonder if this shows the exact buffer. Yeah, it actually shows you the buffer mask and buffer content, which is great. So if you know there's something wrong with the material sRG, you can literally just go here and check the values and make sure the values are correct. You can even check the SRVs, which are all your SRVs. They're all named correctly, so you should be able to track them correctly. The samplers that are used, the input parameters, output parameters, and your resource slots. Oh, okay, I see. These are all the resource slots used. Wow. For the output merger, you can actually check your view information, your blend state, for your depth stencil, and pretty much if you're doing some sort of alpha bending, you want to make sure this is all accurate here. And that's pretty much it. Like you can actually use this for any draw call and any pass. So once you want to first isolate the problem is with a specific pass, then you can debug a specific draw call and try to isolate where the issue is coming from. Actually, one thing I want to see is if I saw something around, you can profile shaders. Oh, okay. I guess it's it's not working right now. Yeah, sometimes this stuff is a little bit finicky. It will work, and sometimes it will not. So make sure you're on the latest drivers and on the latest version of Nsight. That will ensure that, for the most part, this stuff will work. And that's it for my clip. Thank you. Next, we will take a look at RenderDoc. RenderDoc can be used to capture profiling data, as was seen in the previous section on GPU profiling, but it's actually more often used to help debug rendering artifacts. It can be downloaded from the web link provided on this slide. In order to enable pix markers and RenderDoc, you will want to configure your O3DE applications with the following 4 CMake options. In fact, I have these options enabled all the time as a graphics engineer. So you will want to have -dly_pix_enabled equals on, -dly_pix_path, which points to the folder where WinPix event runtime was unzipped, -dly_renderdoc_enabled equals on, -dly_renderdoc_path, which will point to the folder where RenderDoc was installed. And then when you're launching the app, you will want to use the command line option -enable RenderDoc. Next, I'll give you a quick demo on how we can use RenderDoc to inspect data related to every pass and every draw call. Okay, so for this clip, I'm going to be using RenderDoc as a way to show how we can use it to debug rendering artifacts. I've launched RenderDoc as an administrator. I will be launching the application in question. In this case, it's just a simple automated testing.game launcher. I will be loading the default level and the DX12 backend. So everything looks good. And I'm going to say launch. This should launch the application. It's a very simple scene with a shader ball. And I will now capture the frame. After you capture the frame, you can really quickly open it and get a quick overview of what the frame looks like. So in this case, what this merge represents, it represents one command list. So we group a bunch of passes, and then we allow one command list to encode GPU commands for multiple passes. If you expand any one of these, so this is one command list that's going to work for all of these passes. And then you can inspect each one of these passes to see what's going on. So the depth pre-pass is essentially doing the depth pass. And here you go, it's building out your MSAA depth stencil buffer. And so this is probably just the floor, and then this is the shader wall. And these are all the shadow cascades. And you can take a look at the light culling, remap. Let's say something's wrong with the way the shader ball looks. And we would probably want to check the forward pass first. So we'll look at the forward pass with the shader ball, which in this case is this draw call. You can actually see the output, the render targets. So you can even see that if you want to make sure that this is the right draw call for your shader ball, you can use a mesh viewer, and you know that this is the shader ball that's getting rendered. This is how it looks like as a VS output. This is all the vertex shader input and output that you can use if the problem is with the mesh itself. You can look at the texture viewer, so you can actually open up this render target, and let's say there's some problem with the ball. Then you would want to take a look at the pipeline state, which is the pipeline state tab. So you have your input IA information, you have your vertex shader, you have your rasterizer, pixel shader, and output merger. You will basically, for the most part, I end up looking at, I spend a lot of my time in the pipeline state, because usually the problem is always with the vertex shader or the pixel shader and all the resources that get bound for these shaders. So you will want to take a look at the samplers, all the resources, like so these are the constant buffers, these are all the SRVs and UAVs. You will want to take a look at that the data inside is correct. So you can actually open up these constant buffers and take a look and make sure the values are all correct. So this is the materials. Something's wrong with one of the material SRGs, you can make sure that the value is correct here. So, so this is a really good way to debug every draw call and every resource that is getting sent to the GPU and used by the GPU to then apply the shaders. So in this case, this is the shader that's getting run. I don't have the debug symbol, so you can't actually see. You just have the disassembly view here. But you can actually generate shader debug symbols and attach them here. But in terms of the resources, you can actually see all this is a BRDF map. This is one of the render targets. This is like these are all the SRVs that are being used by this path, or UAVs. Actually, I'm not sure which one's which in this case at this point. But yeah, so you can use this to debug any GPU artifact for your thing. And that's it. That's cool. Next, I will go over the in-game path reviewer. It's implemented across all the backends. So it's a great tool for the Steam platforms. You can enable it using the ImGUI menu by pressing Control plus Home. And then you can press Add-in Tools and click on Path Viewer menu option. This will let you traverse all the passes in the frame and all the input and output attachments. And it's a great way to debug something when you have the scene running and you don't want to use an external tool and do all the setup around an external tool. Okay, so for this clip, I will be showing how you can use the in-game patch reviewer to help debug rendering artifacts. So imagine if you don't have access to Nsight or Pix or RenderDoc. This is another possible option. It's not as ideal because the information that you get is limited. You can only see the pass attachments, but it's still something. So I'm loading an automated testing level with the default level with the Vulkan backend. The patch tree viewer should work on DX12, Vulkan, and Metal. So all the platforms in theory can run. It's just easier to use on Steam platforms because your screen real estate is quite big. Oops, I haven't even launched it. Let me launch it. But if you were imagine if you were using it on a mobile device, it would be a lot harder to traverse the menu and the whole patch tree for the frame. So it's just a lot easier to use on PC or Linux or Mac. So it's hooked up to the in-game menu. You would press Control Home, and it will bring up the in-game menu. You press Add in Tools, Patch Viewer. This is the patch tree. It shows all the patches that are being run in the frame. You can enable preview attachments, show the attachments, and then pretty much now, let's say the problem is with the forward pass. I can go to the opaque forward pass. These are all the inputs. These are all the outputs. These are all the input attachments and output attachments. So input for the forward pass is the BRDF map, the full screen shadow render target that was calculated from a previous pass. You have the directional shadow map, exponential shadow map, projected shadow map. The directional one may have, so the color range, you can use this to, here we go. You can use this to, if your render target has a very small color range, you can use this to manipulate that and get better information. You have the tile data for lighting and the light list that's remapped. And you also have a depth step. So I wonder if the depth step shows you the, not right now. So the output of the forward pass will show you your diffuse output, your specular, albedo, wonder if albedo, yeah, we can change the color range, and normal. So yeah, so you can use this viewer to look at attachments if you don't want to go through the process of hooking up an external tool. And that's it for the demo. And that concludes the end of this talk. I've posted an O3DE wiki, which contains pages on GPU profiling and GPU crash-related debugging. We also have an O3DE Discord server, and there are multiple SIGs, and one of the SIGs is set up for graphics-related discussions. It's called SIG-graphics-audio. Please join that SIG and post any questions you may have related to this specific talk or anything related to rendering in general. And hopefully me or somebody from the graphics community will be able to answer your questions. Thank you.